Lesson: Graph Theory and Network Analysis in AI Contexts. Graph theory and network analysis are pivotal in the field of artificial intelligence, particularly in understanding and solving complex problems related to connectivity, hierarchy, and optimization. These mathematical structures are essential in representing and analyzing networks of interconnected entities, which are ubiquitous in AI applications such as social networks, recommendation systems, and transportation logistics. The study of graphs allows AI practitioners to model relationships and interactions within data, offering insights that drive decision-making and strategic planning. Graphs are composed of nodes and edges that connect pairs of nodes. This simple yet powerful abstraction enables the representation of a myriad of systems and problems, from traversing social networks to optimizing routes in logistics. Network analysis involves the exploration of these graphs to extract actionable information, such as identifying key influencers in a social network or detecting communities within a dataset. In AI, graph theory often intersects with machine learning and data mining, where graph-based algorithms are used to enhance the learning process by capturing dependencies and interactions that traditional methods may overlook. One of the most compelling applications of graph theory in AI is in recommendation systems. Platforms like Netflix and Amazon leverage graph databases to store and analyze user-item interactions, enabling them to provide personalized content recommendations. This approach is particularly effective because it considers not only the direct interactions between users and items, but also the implicit connections that arise from shared user behaviors and preferences. Graph-based recommendation systems often employ algorithms such as PageRank, which was originally developed by Google to rank web pages based on their link structures. By treating users and items as nodes in a bipartite graph, these systems can identify influential nodes and infer preferences, leading to more accurate and relevant recommendations. In addition to recommendation systems, graph theory plays a crucial role in natural language processing, an area of AI concerned with the interaction between computers and human language. Dependency parsing, a common NLP task, involves analyzing the grammatical structure of a sentence by identifying the dependencies between words, which can be naturally represented as a graph. Graph-based methods have been shown to improve the accuracy of dependency parsing by capturing the hierarchical structure of language. This has significant implications for tasks such as machine translation and sentiment analysis, where understanding the nuances of language is critical. Graph neural networks represent a significant advancement in integrating graph theory with deep learning. GNNs are designed to operate directly on graph structures, allowing them to capture the spatial dependencies and topological properties inherent in graph data. These networks have been successfully applied in various domains, including drug discovery, where they are used to model molecular structures as graphs and predict their properties. By leveraging the relational information encoded in graph structures, GNNs can provide more accurate predictions compared to traditional neural networks, which typically require data to be represented in grid-like structures. Practical tools and frameworks have been developed to facilitate the implementation of graph theory and network analysis in AI contexts. NetworkX, a Python library, is widely used for the creation, manipulation, and study of complex networks. It provides a comprehensive collection of graph algorithms, from basic operations like adding and removing nodes to more complex tasks such as community detection and centrality analysis. By integrating NetworkX with other data science libraries like Pandas and NumPy, practitioners can perform sophisticated network analyses that are both efficient and scalable. Furthermore, graph databases such as Neo4j offer powerful solutions for storing and querying graph data. Unlike traditional relational databases, which can struggle with complex relationships and queries, graph databases are optimized for traversing networks of interconnected data. This makes them ideal for applications that require real-time insights from large and complex datasets, such as fraud detection and supply chain optimization. Neo4j's Cipher query language allows users to express complex graph patterns succinctly, enabling the efficient retrieval of meaningful information from large datasets. In the realm of network analysis, community detection is a technique used to identify groups of nodes that are more densely connected to each other than to the rest of the network. This is particularly useful in social network analysis, where communities often represent groups of users with shared interests or characteristics. Algorithms like the Louvain method and spectral clustering have been developed to identify these communities, providing insights into the structure and dynamics of social networks. By understanding the community structure of a network, organizations can tailor their marketing strategies and improve customer engagement. Graph theory also offers solutions to optimization problems commonly faced in AI applications. For example, the traveling salesman problem is a classic optimization problem that seeks the shortest possible route for a salesman to visit a set of cities and return to the origin city. This problem can be represented as a graph, where cities are nodes and roads are edges. Although TSP is NP-hard, meaning it cannot be solved in polynomial time, heuristic algorithms such as genetic algorithms and simulated annealing can provide approximate solutions that are sufficient for practical purposes. These algorithms are widely used in logistics and transportation to optimize delivery routes and reduce costs. Despite the versatility and power of graph theory, challenges remain in its application to AI. One such challenge is the scalability of graph algorithms, particularly when dealing with large-scale networks that contain millions of nodes and edges. Recent advancements in distributed computing and parallel processing have helped address some of these issues, enabling the analysis of massive networks that were previously infeasible. Tools like Apache Giraffe and GraphX, which are built on top of distributed computing frameworks like Hadoop and Apache Spark, have been developed to handle big data graph processing, making it possible to perform network analysis on an unprecedented scale. In conclusion, graph theory and network analysis are indispensable tools in the AI toolkit, enabling practitioners to model complex systems and extract valuable insights from interconnected data. By leveraging practical tools and frameworks such as NetworkX and Neo4j, professionals can address real-world challenges and enhance their proficiency in graph-based AI applications. As the field continues to evolve, the integration of graph theory with machine learning and data mining will undoubtedly lead to further advancements, driving innovation and improving decision-making across various domains. The ability to effectively apply graph theory and network analysis in AI contexts is a critical skill for any AI professional seeking to remain at the forefront of technology and innovation.